Welcome to the Explainer. Today, we're building with what might be the smartest Lego block ever invented. Seriously, it's a concept that lets engineers predict these invisible forces inside a skyscraper or a jet engine, and we're going to assemble it piece by piece.
You ever look at a massive bridge or an airplane wing and just wonder, how do they know it's safe? How can they be so sure it won't snap? Well, they have to answer this massive question. If you push on it over here, how does that force, that stress, spread out across the entire complex shape?
Well, the secret is actually kind of brilliant. You don't try to solve the whole complex shape at once. That would be impossible. Instead, you cheat. You break it down, you approximate it with a mesh of thousands or even millions of tiny, simple, predictable pieces. You solve for each little piece, add it all up, and you get a stunningly accurate picture of the whole thing.
So that's what we're doing in this explainer. We're going to zoom way in and focus on just one of those pieces. We are going to build the master blueprint for our smart Lego, an element that's famously known as the constant strain triangle.
Okay, first things first. Let's put one of these triangular building blocks under the microscope. To really get how it works, we have to start with its most basic definition. What is this thing, really? So don't let all the math on the screen scare you for a second. At its heart, our element is just a triangle. That's it. It's defined by the coordinates of its three corners, which we call nodes. And there's a rule we always follow. Number them counterclockwise. You'll see why that little detail matters in a bit.
Now here's the really clever part, the big shortcut. When this whole triangle gets pushed or pulled around, we don't even try to track the movement of every single point inside it. Nope, we only care about what happens right at these three corners. Each corner can move left and right, we'll call that U, and it can move up and down, we'll call that V.
This brings us to a term you're going to hear a lot in engineering, degrees of freedom. It's just a fancy way of saying how many ways something can move. So we've got 2 directions for node 1, 2 for node 2, and 2 for node 3. That gives our simple little triangle a grand total of 6 degrees of freedom.
Okay, so if we only know what's happening at the corners, how on earth do we predict what happens inside the element? I mean, that's where the real magic starts to happen.
We use this amazing mathematical trick. We just assume that any point inside the triangle moves based on a weighted average of how the corners move. Think of it this way. If a point is super close to corner 1, it's going to be influenced almost entirely by corner 1's movement. This means the triangle deforms in a simple, straight-line, linear way. It's a simplification, for sure, but it's the key that makes the whole thing solvable.
And these weighting factors, they have a cool name, shape functions. There's one for each node, N1, N2, and N3. You can think of N1 as kind of like the influence map for node 1. It has a value of 1 right at node 1, and it smoothly fades down to 0 at the other 2 corners. It's this incredibly simple, elegant way to describe how much pull each corner has on the rest of the triangle.
All right, so we've figured out how the whole shape moves. What's the next logical step? Well, now we need to figure out how much it's stretching or getting squished on the inside. In engineering, we have a specific word for that internal deformation. We call it strain.
This is where a little bit of calculus basically gives us a superpower. By taking the derivative, which is just a fancy math tool for measuring how things change, we can precisely calculate that strain. And this whole process cooks up a brand new tool for us, something we call the B matrix. Its one and only job is to be a translator. It takes the 6 corner movements we know and translates them directly into the strain happening inside the element.
Okay, stop. This is probably the most important insight of this whole thing. I want you to look closely at the recipe for that B matrix. I mean, really look at it. You see the coordinates of the corners, right? x1, y1, x2, y2. But tell me, what's missing? Do you see a plain old x or y variable anywhere in there?
Nope, there isn't one. And that is the big aha moment. The fact that x and y are totally absent means the strain doesn't change depending on where you are inside the triangle. It's the same everywhere. It's constant, and that is why it's called the constant strain triangle. It's a huge simplification, but it's what makes the math work.
So let's recap. We know how it moves, we know how it deforms. What's the final step? We have to define its personality. How tough is it? How much does it fight back when you try to push it? We need to define its stiffness.
And that brings us to the grand finale, the element stiffness matrix, which we call K. You can literally think of this thing as the element's unique DNA. It's a 6x6 grid of numbers that acts as the complete instruction manual. It tells us exactly how much force we need to apply at any corner in any direction to get a certain amount of movement. And I know that equation looks intimidating, but trust me, it's just a recipe with 3 core ingredients. First, you've got the element's physical size, its thickness and area. Second, there's our old friend the B matrix, which basically describes the element's shape. And finally, something called the D matrix, which is just a number representing what it's made of. Is this Lego made of steel, or is it made of rubber?
And that's it. Just like that, our smart Lego is complete. We've built this fully defined, totally predictable package. We know its geometry, we can predict how it moves, we can calculate how it deforms, and we know exactly how it resists force. It's now ready to be connected to thousands of its neighbors.
Which, of course, leaves us with one last giant question. We've perfected a single building block, but the real magic, the real power, comes when you assemble millions of them. How do you write the instructions so that every single piece connects perfectly and the entire structure works together as one? Well, that's the next and most powerful chapter in the story of finite element analysis.